Hi, I'm Alvaro Calafell, and in this second video about harmonics and electric power systems, we will explain what harmonics are. In the first video, we talked about power quality and we saw that harmonics are voltage disturbances which distort sinusoidal voltages and damage power quality. In the present video, we will explain the origins of harmonics. For that, we must analyze separately harmonic currents from harmonic voltages, because although they are related, their origin is different. We will start explaining harmonic currents and their origin, leaving harmonic voltages for the next video. Harmonic currents are produced by nonlinear loads. Broadly speaking, there are linear and nonlinear loads in electric power systems. Linear loads consume similar currents when they are supplied by sinusoidal voltages, and they do not modify the sinusoidal characteristics of currents in networks. Examples of linear loads are incandescent lamps, which are electric lights with a wire filament heated until it glows; non-saturated motors, which could include motors that are directly connected to the grid; and resistive loads, which take into account any load which relies on the Joule effect. Nonlinear loads consume periodic but non-sinusoidal currents when they are supplied by sinusoidal voltages, and then they introduce these distorted currents into the network. Examples of nonlinear loads are electronic loads such as rectifiers, discharge arc loads like for example gas discharge lamps, and saturated inductance loads, which can be motors or transformers for example. Although it is clear that nonlinear loads modify the sinusoidal waveforms of currents in electric power systems, the question would be where and what are harmonics? We will answer this question in the next slide. The Fourier series theorem states that any periodic non-sinusoidal function can be written as the sum of sinusoidal functions whose frequencies are integral multiples of the original function frequency. According to this theorem, this typical periodic but non-sinusoidal current of frequency 50 Hz, consumed by single-phase rectifiers, can be written as the sum of a sinusoidal current of the same frequency as the original waveform, which is called the fundamental current, plus other sinusoidal currents of frequency 3 times, 5 times the frequency of the original waveform, also called the fundamental frequency. These waveforms are the harmonic currents, which distort the fundamental current and are introduced into the network. The harmonic order of these currents is the integral multiple which multiplies the fundamental frequency to obtain the frequency of the corresponding currents. For example, this is the third harmonic and this is the fifth harmonic. We can obtain the harmonic order by dividing the frequency of the harmonic current by the fundamental frequency. This can be analytically expressed as follows, where the sinusoidal currents are characterized by their frequency or the harmonic order, the peak value of the current or the root mean squared value, and the phase angle. These currents can also have an IP0 value, which is the waveform's mean value, although this value is usually 0 in electric power systems. Considering the previous explanations, the current consumed by a single-phase rectifier can be expressed by adding the fundamental current, the third harmonic current, the fifth harmonic, the seventh harmonic, and the ninth harmonic current. Other examples of the Fourier compositions are shown in the following slide. The first waveform corresponds to the current consumed by a single-phase rectifier. The second corresponds to a typical two-peak current consumed by a three-phase rectifier. We can see in the plots the fundamental and the harmonic currents. The characteristics of these currents are shown in the tables below. In this video, we have gone over the origin of harmonic currents, and in the next one, we will talk about harmonic voltages and their origins.